Welcome, and thank you for joining this webinar, Invisible Power, Infinite Scale, How Ambient Energy is Pushing the Battery-Free IoT World, prepared by Alpert research team.
Let's zero in on the source. How exactly do we harvest this invisible power? You structure the process into 4 sequential phases.
This systemic view is essential for robust design. Number 1 is availability assessment. This is the survey stage. Before deployment, engineers analyze the environment. Is the primary source light, and what are the diurnal patterns? This dictates the choice of harvester. 2 is energy conversion optimization. This is the engineering layer. You have to select the appropriate transducer and then maximize its output. 3 is energy storage. Buffering the converted energy, typically in those CSCs for AIoT, making sure it's ready for use. And finally, 4 is power management and consumption. This involves regulating the DC flow, managing the cold start sequence, and protecting the device from voltage instability. Okay, let's shift to the energy sources themselves. We know the components that do the conversion are called transducers. What are the 2 main KPIs, the key performance indicators you'd use to evaluate a transducer?
The 2 you always have to look at are power density and conversion efficiency.
So how much power you get for its size?
That's power density, milliwatts per square centimeter, for example. And then conversion efficiency is just what percentage of the energy hitting the transducer actually gets turned into useful electricity. The best choice always depends on the environment. Moving to photovoltaic, or light energy, the largest projected source. It's mature, but the indoor application presents some unique challenges compared to standard rooftop solar.
The challenge is spectrum and intensity. Indoor light is low, often fluctuating between 100 to 500 lux, and it's dominated by artificial LED or fluorescent lighting, which has a very narrow color spectrum. Traditional high-efficiency silicon PV is optimized for full-spectrum sunlight. This has spurred research into alternatives. Amorphous silicon is better at converting low light, and advanced materials like organic photovoltaics, or OPV, are being specifically developed to match the indoor light spectrum, maximizing conversion efficiency under those specific conditions. Kinetic or mechanical harvesting. This seems perfect for things that are always moving.
Mechanical is all about converting motion, vibration, or strain into electricity. The power you get can vary a lot.
And the main transducers are?
Piezoelectric elements are a big one. They generate a charge when you bend or squeeze them. And the other newer one is triboelectric nanogenerators. TINGs.
They generate power just from friction.
It's a bit more than just friction. It's a combination of what's called triboelectrification, which is the static charge that builds up when 2 different materials touch and separate, and electrostatic induction. So as the 2 materials move apart, you create a charge imbalance, a difference in electrical potential, and that drives a current. They're fantastic for harvesting low-frequency, irregular motion, like someone walking. But the key technique in many of these is called magnetic plucking.
What's that?
It uses magnets to quickly snap the harvesting element back and forth. This increases the energy you get, but it also reduces mechanical wear, which is obviously critical if you want this thing to last for 20 years on a bridge.
Thermal energy, using thermoelectric generators, or TEGs. This uses the Seebeck effect, which needs a temperature difference.
The Seebeck effect is fascinating. A temperature difference across a special material creates a voltage. You can get a decent amount of power, but the constraints are pretty significant. First, the efficiency is really low, usually under 7%. And second, you absolutely need a stable, sustained temperature difference. If it disappears, your power goes to 0 instantly.
RF energy harvesting, RFEH.
RFEH is absolutely crucial because it works where nothing else can. It uses a rectifying antenna, to capture ambient radio waves and turn them into DC power. It's projected to power about 36% of all AIoT devices. Its limitation, of course, is power density, incredibly low compared to sunlight.
So you need a pretty strong signal to make it work.
Generally, the rule of thumb is you need a signal strength of at least negative 20 dBm, which is about 10 microwatts. Now, if you have storage, you can work with less, maybe down to negative 30 dBm, but it's still a challenge. The good news is, even a weak cellular signal has been shown to provide enough power for these devices.
And this brings us to SWIPT, simultaneous wireless information and power transfer.
SWIP is a game changer for efficiency. There are 2 main ways to do it. The first is called power splitting.
You just divide the signal.
It literally split the incoming RF signal. Some of it goes to the power harvester, and the rest goes to the information decoder. The other method is time switching,
where you rapidly switch between the 2 functions.
Exactly. For a few milliseconds, you're only harvesting power. For the next few, you're only decoding data. You just alternate back and forth very quickly. So to manage this variable power, what essential roles do the power management units, the PMUs, play beyond simple switching?
The PMU is the brain controlling the device's electrical life. It has 3 highly specific jobs in an AIoT context. First, managing the cold start, the complex process of bootstrapping the device's main microcontroller from a state of 0 charge, which requires careful regulation of voltage ramps. Second, protection guarding against overvoltage that could damage the capacitor or the microcontroller. And third, continuously running that MPPT algorithm to optimize power transfer from the harvester to the storage buffer, ensuring maximum efficiency even as the ambient conditions change rapidly.
I think the key strategic takeaway is that shift in market dynamics. This technology fundamentally transforms what used to be an operational cost for a network operator, blasting out a radio signal, into a monetizable service, providing wireless power. This movement creates new ecosystems where the manufacturers and retailers who actually own the sensor data become the new data hubs. They create value in a way that's separate from just providing connectivity. It forces a total reassessment of where value lies in the entire IoT chain. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert research team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.